Hey everyone, Thrasher here. We are looking at a new way of categorizing forces. It turns out that forces come in two different types, conservative forces and non-conservative forces. We haven't introduced this term before because it's based on how these forces do work, force times displacement, on objects. But now that we know what work is, we're going to introduce this term. This term is also very important as we introduce the topic of conservation of energy. So this video, we're just going over these two different types. It can be a little tricky, so bear with me. Okay, starting off, forces fall into one of two categories based entirely around how they do work. The definitions we have are a little technical, all right? Bear with me. So the following are two technical definitions for if a force is considered conservative. If they match these descriptions, it's going to be a conservative force. If it doesn't match, it would be what we call a non-conservative force. Okay? First, a force is considered conservative when the work it does on a moving object is independent of the path between the object's initial and final position. The other definition, by the way, these are from your textbook, but they apply anywhere. A force is conservative when it does no net work on an object moving around a closed path, starting and finishing at the same point. When I read those definitions, especially when I first read those definitions, I thought, what? This is very unclear. Like I said, these are very technical definitions. I'm going to offer Mr. Thrasher's alternative definition, which certainly might not be 100% accurate all the time, but it's the way I like to think about it. A force is conservative if the work it does can be undone. Okay, and I put undone in quotation marks. This is still not super clear, I admit. We're going to look at two examples, and hopefully that will make it a little more understandable. Very quickly, when I say undone, remember that work can sometimes be positive or it can be negative. If I have a force that can do positive work sometimes, and then I can have it do negative work to kind of subtract, to cancel some work, then it can undo some of the work. And if a force is able to do that, we call that type of force a conservative. If a force can't cancel out, if it can't go back, then we would say it's non-conservative. This is much better seen with an example. So here we go. We're going to look at climbing a ladder. So here's example one. We're going to look at two quick examples, mostly based on diagrams. Climbing a ladder. And we are very specifically going to look at the work done by the force of gravity. And that's the force of gravity right here. It says mg. So the work done by the force of gravity is the force of gravity times the displacement. We saw this in an earlier video. This is how we eventually got at the term gravitational potential energy, but we're not going to focus on that right now. All right. Also, as a reminder, the force of gravity, the weight always acts straight down. So I have a pool here, and this is like the high dive. So let's imagine we have a little kid, okay, or an adult, I guess it doesn't really matter. But the kid is going to climb up the ladder, and, hopefully they're going to jump off and fall into the pool. All right. First, let's imagine when the kid is climbing up the ladder. I can't draw very well, so bear with me. Aha! There they are climbing up the ladder. It looks like a dog walking upwards. Anyway, climbing up the ladder. The kid has a displacement going upwards. This is their displacement d. What direction is the weight? This way. As the kid is going up, the force of gravity is doing negative work. I'm very specifically looking at the force due to gravity. Because gravity acts down, you're climbing up. You're doing, or the force of gravity, I should say, is doing negative work. This kind of makes sense, because when you climb a ladder, it's tiring. When you're doing negative work, you're losing energy. So the kid is climbing, and the higher and higher they go, the larger the amount of work it's going to be. And if you have a larger and larger displacement, the work is going to be more and more negative. So the kid gets to the top. Ta-da. Ha-ha, triumph. And well, okay, the force of gravity just did a whole bunch of negative work on the kid. When they're up here, the work done is negative. Is there any way from Mr. Thrasher's definition, if I go back, is there any way for this work to get undone? And it turns out, yeah. As the kid climbed up, work was very negative, the work done by the force of gravity. When the kid jumps off, when they jump off downward, let's see if I can draw it. Well, now the displacement is downward and the force due to gravity is downward. Here, going down, that is positive work. Gravity does positive work on the kid. And that makes sense because the kid is gaining energy. They're speeding up. By the work energy theorem even, their kinetic energy would be increasing, going faster and faster. So if we started here at 0, okay, the kid started with 0 work. They're climbing, they're climbing, they're climbing, they're climbing up and up and up and up. The work done by gravity is very negative, but then they jump off. And then when they jump off, the work done is positive. When they get back to the pool level, the total work done by gravity is 0. It all cancels out. All right, that matches. So the force done by gravity, here is a key thing you should write down. The force due to gravity. Force due to gravity. So I make a mess. Force due to gravity. The weight. It's a conservative force. It can be undone. So that's an example of a conservative force. Well, let's see if I go down here, let's see if my really much more technical definitions fit this also. The first one said that a force is conservative when the work it does on a moving object is independent of the path between the initial and final positions. Here's what it means. Let's say that the kid started here, and let's say they end here. The work done by the force of gravity is going to be the kid's weight, which isn't changing, times that displacement. And if we call this displacement h, that's the Fw times h. Obviously, if the kid goes all the way up and then they're standing at the top, this is equal to the work. If the kid goes up, let's say they start here, they go up, then they get scared. Then they start going back down. Well, first the work was negative. As they went downward, the work would be positive. They get to here, ooh, they get another dose of courage. Then they go all the way back up. Negative. The work done is still the same amount. They still traveled a height of h. Or they had negative work, then positive, then negative again. They still would have gained that same amount of negative. It doesn't matter. It was independent of the path the kid chose. Whether they went straight up the ladder or up, then down, then up, then down again, up again, down again. Okay, as long as they eventually get to that same spot, as long as they eventually have a displacement of h, whatever they did in between, up and down the ladder, that doesn't matter. So it matches this definition here. And for 2, a force is conservative when it does no net work on a closed path. Closed path meaning the starting and finishing points are the same. Well, I already saw that. If the kid has 0 work at this spot here, they go up, they go up, they go up, that's negative work. And then they fall down, That's positive work. It cancels out because they have negative work going up, positive work going back down, so no net work. So gravity does still match these two more technical definitions. Let's look at another definition, or another example, I should say. You could write down example number 2 if you want. I didn't do that. Example 2. Is friction a conservative or non-conservative force? Think about it. Maybe hit pause, take a guess. So let's say I'm over here, I'm on the left, and I'm pushing on the box. I'm pushing on the box this way. F push. We know that friction, if the box is going to move this way, so here's my H, or my displacement, I should say. Here's my D. I know that if I'm pushing the box to the right, friction is this way. Well, is the work done by friction going to be positive or negative in this case? I don't know what's going on down there. The work done by friction is going to be negative. It's going to be negative because the box is moving to the right, but friction, that force, acts to the left. Well, now let's see what happens if I move the box this way. Here I am trying to undo. See if I can undo that friction. Now the displacement is going to be this way. I'm going to get it back over here. So here's my D again. If the box is moving this way, what direction is friction? Oh, it's pointing now to the right. Is friction here, is the work done by friction positive or negative? It's still negative because friction always opposes motion. I didn't have negative work at one time, positive work in another time. Friction is always opposite the direction of motion. That means friction is pretty much always going to be a negative amount of work done on an object. Friction is a non-conservative force. I can't undo it. If it was negative 10 here, it would be negative 10 here. That's not canceling. That's adding up to negative 20. So friction is a non-conservative force. In fact, most forces are non-conservative. If you think of any kind of pushing force, if you think of like the normal force, very few forces are actually conservative ones. For the most part in this class, especially in the near future, we're only going to be using gravity, the force due to gravity, as a conservative force. Sorry the video ran over, but those are conservative versus non-conservative forces.